Welcome back, class. Today's video is going to answer the question, what's the inverse of a matrix? Now, in last video, we learned about the determinant, and the determinant is important because it determines if we have an inverse. And an inverse is important because that is our way of doing division involving matrices. Now, an inverse is basically an operation or a function or something that takes your inputs and outputs and switches them or gets rid of something going on. So we're really going to work at looking at what an inverse of a matrix is. So in last video, we took the example 2x equals 8. And I said to you, without dividing, how would you solve this? And we all decided we would multiply by 1/2. And by multiplying 1/2, that is the inverse of 2. Because if I multiply those two things together, I get 1 back, okay? So going along with that, I'm going to talk about two phrases with you, or two nouns, if you will. I'm going to talk about the additive inverse and the multiplicative inverse. Now, your additive inverse is the value you add to something that doesn't change its value. So 6 plus what gives me back 6? And that simply is 0. If I add 0 to any number, it gives me back that same number. So before I move on to multiplicative, let's talk about what does that look like when it comes to matrices. What is the matrix I would add to this matrix to not change any of the entries' values? And what it ends up being is a matrix with all 0 as the entries, because that way 5 matches with 5, you get 5. -5 matches with 0, you get -5. -2 matches with 0, you get -2, etc. If I add a matrix of the same exact size with all zeros, I would get back the same exact matrix, which is why this is the additive inverse matrix. Now, multiplicative inverse is a little bit different because multiplying has a lot more rules and procedures in how we actually find out the multiplication between two matrices. Now, numbers, not that bad. What is the number you multiply by a number to get the exact same number back? It's 1, okay? So now I have this 5, -5, -2, 2, and I'm not going to put ones all in here like it might be easy to do. Because if I put a 1 here and a 1 here, 5 would line up with 1, -5 would end up with 1, and I would actually get 0 right there. So what I'm going to do is remember, it's rows here, columns here. So I want 5 to partner up with 1, and I want -5 to go away. And now, to get this guy, I want the 5 to go away and the -5 to stay. This is the matrix that if I multiply this times this, I would end up with that. And I'll quickly go through this with you. Remember, when you multiply, you only want rows from here, and you want columns from here. So if I would multiply these guys out together, I would take 5 and -5 times 1 and 0. So 5 would partner with 1. Always add the partners when you multiply. -5 would partner with 0. And if I add those together, 5 plus 0 would give me 5 right there. And so on and so forth. Row 1, column 2. 5 would partner with 0, and -5 would partner with 1, because I'm doing column 2 answer here, row 1, column 2, and I would get 0 and -5. Same thing here, -2 would be with 1, and +2 would be with 0. This would cancel out, -2. -2 would be with 0, and 2 would be with 1. That's how I'd get the 2. So it's not a matrix of all ones. Multiplying has rules. So this right here is a nice identity matrix. This is who you would multiply by to be like multiplying by 1. This guy's really important. Likewise, if I have a matrix and its inverse, if I would multiply by each other, kind of like here, these two things multiply, give me 1. If I would take a matrix and its inverse, I would end up with this matrix here, which we're going to come back and revisit that in a minute. But first, we're going to actually use some formulas. In the last video, we used this formula, the determinant. The determinant is the difference of the diagonals. A times D minus B times C. It's nice. It reminds you of cross multiplying as far as you make an X with them, if you will. So I kind of like that here. Remember your notation. You'll either say DET of A, absolute value sign of A, or I'll just plain old say, what is the determinant? Now, the inverse is a little tricky. When you find the inverse, by the way, this is the notation, just kind of like Algebra 2 was, not kind of like, exactly like. Remember we did inverse here. Here's the inverse of matrix A. Now, this can be any matrix. You can call B, C, D, any capital letter stands for a matrix, if you will. 1 over the determinant. You're going to take the fraction here and you're going to multiply it out times each of these entries. Now, if you notice, those entries are not in the same position. What ends up happening is the first diagonal changes position. So D goes where A goes where D is. And the second diagonal simply changes signs. So if it was positive, it'll now be negative. If it was negative, it'll now be positive. So let's put this into action so we know what's going on. I'm going to call this matrix A because let's just do this. The first one says, determine whether the matrix has an inverse, and if so, let's find its inverse. So determine, determinant. Let's do this. The first thing I'm going to do is determine if I have a matrix. So I'm going to find the det of A. The det of A is diagonal minus diagonal, the difference of the diagonals. So 3 times 2 minus 1 times 4. 3 times 2 is 6. 1 times 4 is 4. The determinant of this matrix is 2, which means yes, it has an inverse. So if yes or if so, let's find the inverse. So we want to find a inverse. I'm going to come over here. The formula is 1 over the determinant. So it's going to be 1 over 2. Then I'm going to put the matrix. First diagonal changes position. So 3 and 2 are going to swap. Press pause if you need to look at that a little bit longer. 1 and 4 are going to stay where they are but change signs. So 1 that was positive is now negative, and 4 that was positive is now negative as well. So here's the setup plugged into the formula. All right, so I'm going to take this and distribute this out, which is why we learned scalar multiplication. 1/2 times 2 is 1. 1/2 of negative 1 is negative 1/2. We'll just leave it like it is. It's just negative because of the negative. 1/2 of negative 4 is negative 2. And 1/2 of 3 is 3 over 2. Or 1.5 if you want to do the decimals. I really don't mind. So the inverse of the matrix 3, 1, 4, 2 is this guy right here. And if I would take this guy right here, 3, 1, 4, 2, and multiply it by its inverse, if I would take A times A inverse, I would get back 1, 0, 0, 1 if I multiplied them, because they cancel out and leave me with 1. So this is like 1. All right, so the inverse is really important. We love the inverse. So let's go on to the next one, letter B. I'm going to call this big B, which just means now this is B and this is B. I just don't want you to always be using A. You can use any letter, so I'm going to mix it up a bit. So the first thing I'm going to do is find the determinant of this big old B matrix. So the determinant determines if I actually can find the inverse, so here I go. The determinant of B, the diagonal one is 4 and 3. 4 times 3. Determinant is difference. 2 times 6. 4 times 3 is 12. 2 times 6 is also 12, which means, dun, 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 we have no inverse. It doesn't exist. Okay? So, the good thing is we're done. Let's work. The bad thing is this matrix here we can't divide with, so we're stuck where we are. All right, let's switch and do this last one. Again, I'm going to change letters. I'm going to call it C. That'll make this a C and this is C. I just don't want you to get used to one letter, so that's why I'm mixing it up. So this is like the compatibility test. I'm going to find the determinant of C, the diagonal, difference diagonal. You can have this up anytime you want when you do these. I'm not checking if you were using formulas. I'd prefer you to. All right, negative 8 times 2 is negative 16 minus negative 3 times 4 is negative 12. Two negatives make a positive, so it becomes negative 16 plus 12, which is negative 4, which means, yes, I keep going, and I use this formula. Remember, I'm replacing this with C. So C inverse is going to be 1 over negative 4, 1 over the determinant of C, which is negative 4. And now I'm going to move things around. First diagonal changes position. So 2 goes there, negative 8 goes there. Second diagonal, this becomes 3, and this becomes negative 4. Now I just simply distribute that out to find out what C inverse is. 1/4 of 2 is 2 over negative 4. 3 times that will be 3 over negative 4. This will be negative 4 over negative 4 and negative 8 over negative 4. And honestly, you can leave it like this, but you should try and simplify. This should be negative 1/2. This should be 3 over negative 4. And I don't really mind if the negative's on top, bottom, or floating out front. This should be positive 1, and this should be positive 2. So this is C inverse. Oops, equals. All right, there's one more for you to try. I'd love you to try this without me going over it, and press pause now and try it. I'm going to quick go through the answer just to kind of show you. So press pause so you're not doing this. Let's call him D. Negative 3 and 7 are my first diagonal. Difference for determinant. So this becomes negative 21 plus 18, which is negative 3, which means, yes, I have an inverse. So keep going. Yes, keep going. My inverse of D will be 1 over, and if you have to flip back to the formula, go ahead. Negative 3. First diagonal changes position. Second diagonal changes signs. This 3 is now negative. This 6 is now positive. So it is going to be 7 over 3 negative, positive 1, negative 2, and positive 1. This right here is my final answer. All right, there's more practice attached to the worksheet. Please take advantage. Find the inverse by hand of a 2 by 2.